Okay, let us resume with our second lecture. And during this lecture, we shall introduce tools associated with the conformal method in order to deal with the Einstein Constraint equations and start with our analysis of the resulting PDE system. So we will start just with the Gauss-Codazzi constraints, these two here. And then we will go slowly towards more complicated systems, such as the electromagnetic case that we saw in the previous lecture. So starting here, let us recall that epsilon denotes the energy density induced by our particular physical model, and J, the momentum density. These are defined in this way, where N is the future pointing unit normal vector field to our Cauchy surface. Okay. We will adopt some notations in order to simplify things. We will denote the mean curvature by tau, and for us the mean curvature is not normalized, so there are no dimensional coefficients in front of the trace of the extrinsic curvature. And the first things to note is that these two equations can be thought of as equations for the intrinsic metric and extrinsic curvature with prescribed physical sources epsilon and j. And in this context, these equations would appear as a highly underdetermined system, both for these variables. And this gives us quite some freedom in order to try to split the metric and extrinsic curvature in some clever way, in order to transform this underdetermined system into some determined system of elliptic PDEs. And this is what the conformal method tries and succeeds to do. So let us start with this strategy. And the prescription associated with the conformal method is the following one. We start with a Riemannian manifold, and everything that is here in red is a prescribed quantity a priori, and then we have to solve for what is remaining. So we fix a conformal class here, and we look for a conformal factor to fix our physical metric on our Cauchy surface. And then we split extrinsic curvature into its traceless part here. This K tilde is a traceless tensor, and its trace parts that consist on the mean curvature, basically. And then the traceless parts undergoes one further splitting. That is this one here, where we have introduced this operator that is called the conformal killing operator. That is basically the conformal analog of the derivative. So X is a vector field for us. And basically the kernel of the conformal killing operator consists of conformal killing fields which generate conformal isometries. And then we have another free part to prescribe, that is this U tensor field. And this is at what's called a TT tensor field, and TT stands for traceless and transverse. And the transverse condition is imposed by being divergence free. So here we are prescribing arbitrarily a conformal class, the mean curvature of initial data sets, and the TT parts of the extrinsic curvature here. And we want to solve the constraints for a conformal factor and for this vector field entering in this splitting here. Okay. Then the idea is to appeal to well-known conformal transformations, both for the scalar curvature and for this other operator here, the divergence on a symmetric tensor field. This can be checked as computational exercise. So we know that the scalar curvature of the physical metric solve the constraints is related with our prescribed metric gamma by this relation here. And then the divergence of the extrinsic curvature is related to the divergence of the traceless parts taken with respect to the fixed metric gamma by this expression here. And then the idea is to plug these two expressions into the Gauss-Codazzi constraints. And one sees by direct computation that the Gauss-Codazzi constraints get translated into these two. Basically, the first one here is the energy constraints, and this is the momentum constraint. And here we have introduced some further notation. This operator that appears here is a second order elliptic operator that is called the conformal killing Laplacian. We will refer to it shortly by this name here. And it is defined in this way. It takes vector fields on M and gives us one forms, and is given by the divergence of the conformal killing operator. And here, this operator, which is well known from conformal geometry, we will denote it typically by this L sub gamma, and it's also known as the conformal Laplacian. And here, the important thing, there are a few important things to realize, is that these two equations now form an elliptic determined system for the conformal factor on the vector field X. And this system, if we fix our sources, if we fix epsilon and j, it seems to be posed for these two quantities. A priori, this system is clearly coupled, but as we will see, there are a few simplifying assumptions that decouple the system. In particular, what we should notice is that our conformal splitting is going to typically impose certain conformal scalings for the physical sources, for epsilon and j. We saw that the energy momentum tensor field depends on the metric, and so the physical sources are going to scale with these conformal transformations. And in particular, one can directly notice that, for instance, if we were to have this kind of scaling for the momentum sources, where here this j tilde is constructed with a fixed conformal data, quantities that have a tilde on top will be constructed with the conformal data that is fixed. So with this scaling, this leaves us only with some fixed datum. And furthermore, if we were to impose a CMC condition, so a constant mean curvature condition, then this term would be 0. And this equation would be decoupled from the first one and would leave us with a linear second order elliptic equation that we can analyze, analyzing the mapping properties of the associated operator. And the core of the analysis would reside on the analysis of this equation that is called the Lichnerowicz equation. And these kind of scalings, as we will see shortly, they are quite common, they are natural, and they are called York scalings. And so under these kind of conditions, we can simplify the problem further and just have to deal with this kind of semi-linear PDE. So these are a few of the remarks that we were making before. So the system is posed for these variables with this fixed data. And this is the special case that we were discussing of York scaling, where the resulting equation for the momentum constraint, if we impose a CMC condition, is this one. So the main difficulty in this case is associated with the Lichnerowicz equation. Let us comment on some examples, which is instructive. And so let us start with scalar field and recall that the energy momentum tensor field associated with it has this form here. We are taking the bars from some of these quantities whenever possible in order to lighten the notation. And direct computations show us that the energy and momentum densities are given by these expressions, where this is the momentum density associated with the scalar field and is denoted by pi. And then the first issue is to see how these forces scale when we make our conformal transformations. And since the momentum density depends, for instance, on the normal vector field to our Cauchy surface, this is going to scale. And in particular, it's going to scale with lapse function. So we have to pick up a prescription for how the lapse function associated with our space-time splitting is going to scale under conformal transformations. And there is no unique way to do this, but a quite popular way that is very useful is this choice of densitized lapse. And in that case, we merely prescribe that lapse scales in this way under conformal transformations, where again, this n tilde is our prescribed datum and n is the physical lapse. And so adopting this prescription, And using our conformal transformations for the metric, one can see that the energy and momentum densities scale in this way, where the tilde quantities again are constructed with fixed data. And in particular, one can see that the momentum constraint, the momentum source here is York scale. So this would be a kind of source that under a CMC condition decouples the momentum and the energy constraints. Then let us analyze the case of fluid sources, a perfect fluid, and recall that the energy momentum tensor field is given by this form, where this is the energy density, the pressure density, and the velocity field associated with our fluid. And again, one can directly compute that the momentum density here and the energy density are given by these forms. And we need to analyze the scaling properties, and this is again quite straightforward once we have adopted our conventions. Again, we know how the normal vector field scales because of our choice of densitized labs, and also how all the other quantities scale. What one finds is these two expressions here, where the fluid parameters, in particular the velocity, scales in this way, where the U tilde I, which is the tangential projection onto M and its normal component, the U0, are actually taken to be units of unit speed with respect to this background metric, which is fixed. Okay. And in this case, one can check directly that these sources, as they stand, they are not York scale. So when we couple, for instance, fluid sources, we are not going to be able to naturally decouple the constraint equations. Now let us comment on the case of electromagnetic sources. This is again one case that is going to be of particular interest for us. And in this case, the energy momentum tensor field is given by this expression, where F denotes the two form that describes the electromagnetic field in space-time. And again, it's a computational exercise to see that the energy density is given by this combination of the contributions of the electric field and magnetic fields, and this is the momentum density. And now we have to analyze the scaling properties once again. And one thing that we should realize is that since F tilde is the restriction of the two form F to tangent vectors to M, and F is metric independent, in particular, F tilde is not going to inherit any natural scaling. So F tilde isn't going to scale under conformal transformations, but the electric field is. So in this case, the electric field depends on our scaling for the Labs function, as we saw in the previous lecture. And using the choice of densitized Labs, one finds that this is the scaling associated with the electric field, where again, this vector field tilde is our data, and actually is going to be one of the unknowns that we have to solve for in the conformal method. So the energy and momentum densities after these scalings can be written in this form, where A tilde is what we have to solve for in the electric constraint that we saw in the previous lecture. And here again, since the electric constraint involves these diversions of the electric field, we have to see how this scales under conformal transformations. Again, this is a straightforward computation. And what is interesting is that if we remember that this has to equal something related with the charge density, in the case of electrovacuum, where this is 0, the associated constraint is this divergence equal to 0, and then this constraint is going to be conformal invariant in the case of electrovacuum. And therefore, in this situation, these constraints obviously decouples, and we have to a priori fix the electric field and then use it as an input in the Gauss-Kodazzi constraints equations. Now, if we put these things together, as we did in the first lecture, and if we mix, for instance, a fluid and an electromagnetic field, Then the energy densities are going to be given by a combination of the fluid contributions and the electromagnetic contributions, and the same for the momentum densities here. And in this case, as we saw in the previous lecture, since the matter that is sourcing the electromagnetic field is going to have a particular scaling, this is going to inherit scalings for the charge density that enters into the electric constraint. And we have to evaluate how this scales. And in the case of a fluid with zero conductivity, this is quite straightforward, and one finds this kind of expression. And we will just deal with this case that is the simplest one. And therefore, in this case, using this transformation law that we saw in the previous slide, one sees that the electric constraint now reads as 63. So in this case, since we are not in the electrovacuum case, this is different from zero. This equation couples with the constraints, the Gauss-Codazzi constraints. So if we put together all the examples that we considered before, this would be the energy momentum densities with fluid, with scalar field contributions, fluid contributions, electromagnetic contributions, and the same here, the scalar field contributions, electromagnetic contributions, and fluid contributions, okay? And here we have things that are York scaled, like the scalar field, things that are not, like the fluid contributions, and we have further couplings with other constraints via the electromagnetic field. And in this case, the full system of constraint equation is going to be given by this system 65. And here, these expressions, the small f and the big F, are given by these expressions that merely arise by our previously written, conformally formulated energy and momentum constraints, but we are plugging in these expressions explicit for the energy and momentum densities. Doing that, we have this little f given by these contributions, where this is going to be a scalar curvature term. Then we have these contributions related with the scalar field and the dt part of extrinsic curvature. This is going to be related to the mean curvature and the electromagnetic contributions. And similarly here, the scalar field, electromagnetic, mean curvature contributions, and fluid contributions, okay? And so the Gauss-Codazzi constraints are coupling with the electromagnetic constraints here. One thing that we should notice is that the magnetic constraint is the only one that always decouples. So what this imposes for us is to have to choose a priori F tilde to be a closed 2 form. And then we use this as data in the other 3 constraints that are going to typically be fully coupled. And these are the explicit notations that were above. This small r is basically the scalar curvature term with a term from the scalar field whenever we have a scalar field present. And the mean curvature term here also incorporates some non-scaled sources given by the fluid. This is the momentum constraints given by the scalar field. This is the term that introduces coupling when we are not under a CMC condition, and again, the momentum contribution from the fluid. As we said, this is the only constraints that always decouples, and therefore we have to choose a closed 2 form. Then it's a datum and in their equations. And in order to decouple their equations, typically one has to switch off the fluid contributions. And at least one have to switch off the charge contributions in order to decouple the electric constraint. And if one wants to decouple the other 2, due to the presence of non-York scaled sources, given here, one has also to switch off the fluid contributions. And if one does that, then one falls into this electrovacuum case with no fluid contributions. where now we are redefining the coefficients in this way. So we may have scalar field contributions. And now the electric and magnetic components that are completely decoupled here becomes data in these equations. One has to choose a closed-to form and a divergence-free vector field, and then plug it into these two equations, okay? And furthermore, we see that in this case, since the momentum contribution of the electric field is easier to scale, the momentum constraint is also decoupled from the Lichnewicz equation. So here, again, the procedure is to first solve this equation and then use the solution X to build this traceless part of the extrinsic curvature. And then all the coefficients in the Lichnewicz equations are determined, and we have to solve the semi-linear PDE for the conformal factor. And therefore, there is a minor a priori abstraction here that the well-posedness of the system relies on the momentum constraints being solvable. But assuming it is, this would be the way to go about it. So before going into the main analytic tools related with the analysis of this decoupled system, let us comment on this conformal covariance property that is very important, and it's a very powerful and useful tool for us. And one point that may be intuitive is the fact that there should be some nice relation between solutions that one gets from conformally related data. For instance, if one, instead of starting with gamma, starts with this gamma primed, given by this conformal transformation. And in fact, the relation is explicit and is given, as we will explain now. If one fixes in the complete case where we have fluid contributions, scalar fields, electromagnetic contributions, and so on, if one fixes our fixed conformal data, and one has a solution to the fully coupled problem, from this, we would construct the physical solution to the geometric Gauss-Kodazzi equations by this prescription given by the conformal method, okay? And here we are leaving outside of this picture the data that does not scale, in particular the F tilde and also the fluid parameters, since these don't scale, or the same as the charge density, we are leaving them outside. But with this prescription from the conformal data plus the solution, we build the geometric solution, okay? And such a solution would be a solution of this coupled PDE system, okay? And the point here is that if one were to consider conformally related data, so this, one makes the conformal group to act on our complete set of conformal data, not just on the metric, following this prescription. So we're going to have quantities that scale, and those quantities that did not are not going to scale, the mean curvature, and so on. So one considers this conformally related data for the conformal problem. Then what one can see by direct computation is that if one has a solution associated to the unprimed variables, then applying this transformation rule for the unknowns, for the conformal factor, the traceless part of the extrinsic curvature, the electric field, and the magnetic field, then this is a solution of corresponding to the unprimed conformal data if and only if the primed psi here is a solution associated to the primed conformal data that we just saw here. So we can go from one to the other by applying a suitable rule of transformation under conformal rescalings. And what is interesting here is that the physical and geometric solution constructed following the recipes of the conformal method here are going to be the same regardless if we start with the unprimed or the primed variables. And so this is what we are saying here. And so actually the conformal group is acting like a kind of gauge group here, and the physical / geometric solution is going to be the same in both cases. And all this follows by applying these well-known transformation rules associated with the conformal Laplacian and the divergence of a symmetric tensor field. Okay, this is going to be very useful for us because sometimes we can find a preferred element in our conformal class that simplifies our problem a lot. And this is particularly exploited appealing to the Yamabe classification that we will talk below about, because this controls the sign of the scalar curvature that is the leading term in the Lichnerowicz equation. So this is going to be quite useful for us, and this is in particular quite useful when one wants to construct barriers associated to the Lichnerowicz equation, and we will see this explicitly below. So with all these tools, let us now analyze the decoupled Gauss-Kodassé constraints. And this is the system, recalling our conventions here for each of the coefficients and the dimensional constants. And as we said, the first thing that we need to do here is to solve the momentum constraint that is completely decoupled, so that we can use X to build our traceless part of the extrinsic curvature and determine all of the coefficients in this equation. And this reads as a second order elliptic linear equation, and we can solve it appealing to the mapping properties associated to the conformal killing Laplacian. And these properties are compiled in this theorem here. So given, we are going to in this lecture, we're going to deal always with closed manifolds, and then we will go to some non-compact scenarios. So given a closed Riemannian manifold, satisfying these regularity assumptions for the metric, then this is a mapping from these spaces. Here for us, these are going to be the usual LP-based Sobolev spaces. And all of the properties associated with these spaces, both on compact manifolds and asymptotic Euclidean manifolds, can be reviewed in detail in the lecture notes, as well as the proofs of this kind of mapping properties. Here we're just going to state the theorem and use it. Well, what we know here is that this is going to be a Fredholm map, and in particular, the kernel of this map equals the space of conformal killing fields of the metric gamma. So it's going to, in particular, be an isomorphism if we have a metric with no conformal killing fields. So from this result, one can immediately see a criteria for solutions of this equation. So fixing again a closed Riemannian manifold. Here we should have the hypothesis of this being a closed Riemannian manifold. And assuming that we have this functional hypothesis, then this equation is going to be solvable if the source, which is prescribed here, is basically orthogonal to the kernel of our operator. And in that case, the solution is going to be unique up to the addition of a conformal killing vector. Okay. So these hypotheses are tailored just to guarantee the functional hypothesis that this right-hand side is in LP. And therefore, we have a kind of minor abstraction to solve this equation. And this is given by the fact that this has to be orthogonal to the space of conformal killing vectors of the metric gamma. But this is actually a minor abstraction. Is what one can see that well, one knows from elliptic theory that it's going to be a finite dimensional space, and in particular, the sets of metrics without non-trivial conformal killing vectors are actually generic, and this, for instance, has been shown in this paper here. And so unless we are in a very special situation, typically gamma is not going to possess any conformal killing vectors, non-trivial, and therefore this map is going to be an isomorphism, and this is going to be always solvable. So this is a mild abstraction. And therefore one can typically solve this equation, and then as we said, one has to concentrate on the Lich-Niewicz equation, and the analysis of the Lich-Niewicz equation is based in this setting on two basic tools, the monotone iteration schemes, and then barrier constructions associated with the Lich-Niewicz equation. Okay, and in both steps, the maximum principles are essential. And here let us comment on both the weak and strong maximum principle in this level of regularity. So this is quite similar to the classical weak maximum principle, but just adapted to this level of low regularity. So given a closed Riemannian manifold satisfying this regularity hypothesis, if one considers this equation where this potential, this V function here is in LP and has this non-negativity condition and is not exactly 0, then we have this well-known implication. And let us sketch the proof. The idea is quite straightforward, and the only subtleties that arise are due to the level of regularity that we are dealing with. And the idea is, well, one considers the positive part associated with the solution to this equation. And in particular, this is going to, in our level of regularity, this is going to be in this space. One multiplies this inequality by this function. And the basic idea, what one wants to do here is to integrate this inequality and then to be able to integrate this by parts. And here is where the regularity brings about some subtleties. One has to appeal to certain approximation arguments, and all this is explained in detail in the lecture notes and also in the original paper by David Maxwell. But once we do these steps that are delicate one can guarantee this integration by parts procedure, and one gets this inequality. This is the important part. And since on the support of the positive parts, these two functions are going to equal, one sees from this inequality that this other inequality has to hold. And this, since this is non-negative, this clearly implies that this has to be 0, and therefore the positive part has to be a constant. But if this constant were not going, if it's were not identically 0, then it would be a positive constant over all our manifold. And by continuity of phi, it would mean that phi is a positive constant over all our manifold. But if we do that, when we plug this into the original inequality here given by 71, one would see that this inequality has to hold. Since the constant is non-vanishing, then that would imply that this potential that is non-negative has to be strictly vanishing, but this contradicts the hypothesis that it wasn't. So what we see is that actually the positive part has to vanish identically, and then we get our implication. And the above maximum principle is going to be enough for us for many purposes, but for others, such as when we construct barriers, we're going to need this strong maximum principle. And again, here some subtleties are related with the level of regularity that we are using. And the idea again is if we have a closed manifold and we have the same setting as above, and we have this kind of inequality satisfied by our function phi, then if the function vanishes at a single point, it has to vanish identically. So we're going to be able to use this as a criteria for strict positivity of our solutions. That's something that we want, because our solution to the Lich-Niewicz equation, in order to represent a conformal factor, it has to be strictly positive. And just here to give the idea of the proof, this is more delicate. The idea is a connectivity argument. So we know that the set of points that satisfy this condition are closed, and the idea is to prove that it is also open and apply a connectivity argument to say, to conclude. And in order to show that this, if there is a point that satisfies this condition, then this condition is going to be open. One appears to the weak-Harnack inequality from this paper by Schrödinger. And this actually shows what one wants, and therefore the connectivity implies that either the function is identically zero or it never vanishes. Okay. And the details again can be checked in the lecture notes and also in the original paper by David Maxwell. And so now one wants to analyze this kind of generalized genomics equation, where here these powers I determine the kind of nonlinearities that are present in a specific problem for us in a specific physical model. And we are going to write down the right-hand side typically by this expression f, okay? And what's we're going to assume is that this is defined on some interval of this form, typically, so that this function is differentiable with respect to these variables and is continuous there. So typically we are going to take our interval to have this form with L being a strictly positive number. Good. And one of the last ingredients that we need is the appropriate notions of barriers. So we are going to fix a Riemannian manifold. Here we're always thinking about a closed Riemannian manifold. And we're going to define a subsolution to this equation as a function that solves this inequality. And the super solution is defined using the opposite inequality. Here we have to always be careful that we are using the negative Laplacian. Okay, and so this defines the concepts of sub and super solutions. And then the last ingredient here is related to the mapping properties associated to the conformal Laplacian, okay, or the Poisson operator more generally. So again, this can be checked in the lecture notes and the proofs are compiled there. Here we're just going to use these properties. So we fix a closed Riemannian manifold of this W2P regularity. This condition, as we saw, is always present so as to guarantee that this is embedded in the continuous functions. And this function here, A, is in LP. And we're going to consider this kind of operators that have the same form as the conformal Laplacian. And the idea is that if this function A is, again, is not non-negative and not identically zero, then these operators define an isomorphism acting between these functional spaces. Okay? And so we are going to use this in the well-known monotone iteration scheme. This was first used in this context by Jim Eisenberg, and then it was extended to many other regularity situations by many authors, including David Maxwell, Jorge, and collaborators. And so the idea here is if we fix a closed Riemannian manifold following our regularity conditions, and we consider the equation that we showed above, that is a generalized Lichtenberg's equation. And we assume that this equation admits a compatible pair of sub and super solutions. So sub and super solutions which are positive, and by compatible we mean that the super solution is above the sub solution. Then we can guarantee that there is a solution to this equation that is going to be trapped between the two barriers. So in particular, it's going to be positive. And the idea of this proof is to construct the solution iteratively by solving a sequence of linear problems. The idea is to first introduce a shift in our equation. So we're going to introduce this function A so as to consider this shifted operator. And it's going to be acting between these corresponding functional spaces. And we just saw that this operator is invertible for a choice of A that is positive in particular. And then we want to start an iteration procedure of this form, okay? So we introduce this shift on both sides of our equation. We fix our right-hand side first as data given by putting as an input here the sub-solution. And since this is an isomorphism, we can find first psi1 and then use psi1 as a source and then psi2 and begin an iteration procedure and generate a sequence in this space. And then one proceeds as follows. One first fixes a good choice of this shift function A that is tailored so as to guarantee that this right-hand side has certain monotonicity properties, in particular that it is a decreasing function of psi for any psi between L and M. And this is going to imply through an application of the maximum principle that the whole sequence is trapped between our barriers. And then these put together with some standard a priori elliptic estimates is going to guarantee that our solution, our sequence of solutions is uniformly bounded in this Sobolev space. And then using these facts and put together with Sobolev embedding properties, this guarantees that we can extract a C0 conversion subsequence. So up to a restriction to a subsequence, we have this kind of convergence. And finally, we can again use elliptic estimates to see that this sequence now is going to be Cauchy in the original topology. And therefore, we can extract, again, conversions, but now in the original topology. And this finishes the proof. One applies to the continuity of the operators involved. One can take a limit. And one sees that this limit function actually solves our conformal problem. OK? So one thing that one has to realize here is that we have been able to reduce the problem of analyzing the Lichtenowitz equation to that of finding appropriate barriers for the Lichtenowitz equation. And in order to do that, we are going to need, as we talked before, some results that are well known from the Yamabe problem in Riemannian geometry. So let us just briefly review some results related with Yamabe classification. Let us recall that the Yamabe problem associated here with our Riemannian manifold, it consists in the problem of finding a conformal deformation of a given Riemannian manifold so that the resulting metric has constant scalar curvature. This is classically done on closed manifolds. And due to the conformal transformations associated with scalar curvature, this is equivalent to solving this equation that is known as the Yamabe equation, where here this R tilde is a constant. And if one finds a positive solution to this equation, then this conformal metric has constant scalar curvature given by R tilde. And the first classical observation here is that this equation arises as the Euler-Lagrange equations of this functional, where here this exponent is the critical Sobolev exponent associated to the compact embedding here. And what the kind of variational setting here that one thinks about is a minimization procedure within a conformal class. So the idea is one considers a minimization problem in a fixed conformal class, and then the above functional is actually translated into a functional on the conformal factor that is given by this one here, where this energy is rewritten in this form. And by straightforward computations, one can see that critical points of this functional are going to be weak solutions to the Yamabe equation with R tilde given by this value. And then one also can see, appealing to Holder's inequality and this kind of embeddings, that the infimum of this functional is actually finite. And this number is referred to as the Yamabe invariant, and one can check by straightforward computations that it is actually a conformal invariant. So the standard analysis here is to appeal to variational techniques to be able to find a positive smooth minimizer for this problem. And this problem has been solved by several celebrated contributions, most notably by Yamabe, Schrödinger, Wang, and Shen. And the final resolution of the Yamabe problem implies that the set of smooth metrics on closed manifolds get classified into 3 disjoint classes. And these are according to the sign of the Yamaha invariant, where if this sign is positive, then our metric admits a conformal deformation to constant positive scalar curvature, and we have the corresponding statements for the 0 case and the negative case. And this control on the sign of the scalar curvature is what we want to exploit when constructing barriers for the genomics equation. But in the low regularity setting, this kind of classification is more subtle. In fact, it's in particular more subtle for the case of positive invariant. In the other two cases, one can show that the conformal deformation to constant curvature holds. But well, through notable works here again that can be reviewed, for instance, in this paper by David Maxwell, and also in this other paper by Michael Holstein collaborators, one has an analog Yamaha classification in the low regularity setting. So let us fix a closed Riemannian manifold with our regularity assumptions. And what one has is that the sign of the Yamaha invariant, actually what one can see directly is that it controls the sign of the scalar curvature. Here we're not stating that this can be brought to a constant, but we know that there's a conformal deformation that gives us the sign of the scalar curvature as the sign of the Yamaha invariant. In particular, in these two cases, one can bring by a conformal deformation the scalar curvature to a constant. And in this case, the conformal metric that has the scalar curvature property is given by this metric here. And furthermore, if the scalar curvature is non-negative, then one can only attain a 0 Yamaha invariant if it is strictly, it is identically 0 the scalar curvature. Okay, so let us keep in mind this kind of results concerning the Yamaha problem in this low regularity setting. We will use these results in the next lecture to construct barriers and then apply the monotone iteration scheme in the case of closed manifolds. But let us end this lecture by commenting on uniqueness results associated to the vacuum case. From now on, we are going to concentrate on the vacuum case so as to be more concrete. And within the lecture notes, all these things that we're going to do here for vacuum are done for the general case for the decoupled system, considering scalar fields and also electromagnetic fields. So you can check that in the lecture notes. And so in the vacuum case, we have to consider this equation 82, where now this ATT is given by the traceless part of the extrinsic curvature. We don't have the scalar field contribution. And the same here, this AT is given by the mean curvature contribution, and we don't have the fluid contributions, okay? And this uniqueness result is also essentially due to David Maxwell. And the idea is that if we have a closed Riemannian manifold of the regularity that we are working with, and the coefficients satisfy this regularity hypothesis, then given two positive solutions to this equation, they are either equal or they can be positively proportional if all the coefficients vanish here and we are Yamaha 0. And let us merely sketch the main steps of the proof. The idea here is to appeal to conformal covariance. So we have our two solutions. And one first constructs the physical solution associated to one of these solutions. Here, this G1 is the conformal transformation that goes from the conformal data to the physical and geometric solution. And we know from conformal covariance that the Lichtenberg's equation is going to admit the solution phi1 if and only if this conformally related Lichtenberg's equation admits this solution psi, that now involves the two conformal factors. And also here what we know is that the extrinsic curvature has the scaling associated to the physical solution. So as we were saying, since this G1 and K1 are the physical solutions associated to the geometric problem, then they solve the Gauss constraint that is given by this expression here in vacuum. So one can replace here the scalar curvature term by the right-hand side of this equation. So this can be used here. And then one can send this to the right-hand side to rewrite this equation as follows. Here we can introduce this one, no problem, because it's killed by the Laplacian. And doing as we said above, we get this form for the generic equation. And now the idea is again to multiply this by parts by the positive parts of this expression. And there are some subtleties associated with integration by parts procedure that have to be done with care using approximations, and this is explained in lecture notes. But after integrating by parts the left-hand side, one sees that one here is going to get a sign on the subset of M given by this positivity condition where phi is greater than 1. And on the other hand, one can see directly that on this subset of N, these two factors have a sign when phi is greater than 1. So when one integrates this equation over all of M, one is going to get the opposite sign to the one that we got here on the right-hand side of the equation. So this is going to imply that this has to be exactly 0, as we are seeing in this expression 84. And one can do a similar analysis with the negative part of this function, and one gets the same result. So both in the subset of M where phi is less than 1 and when it is where it is greater than 1, this has to be 0. And since phi is continuous because of our embeddings associated with Sobolev spaces, one sees that this expression has to be constant over all of the manifold. In particular, recalling our definition for psi here, one sees that the two solutions have to be positively proportional. And what one checks directly is that if phi is not identically 1, then one can multiply our equation again here by this expression. The left-hand side is going to vanish because phi is constant. And when one integrates here, one sees that if either phi is greater than 1 or less than 1, one picks a sign on each of these factors. And in particular, these things give us that both terms are positive. And since both terms are in fact non-negative, these factors are positive, this relation implies that the coefficients have to vanish. So what we see is that these two coefficients, if this constant is different from 1, have to vanish identically. And going back to this equation, this implies that the scalar curvature is exactly 0. So the first, since this G1 is a conformal deformation of gamma, we see that from the IMPA classification that our original metric was IMPA 0. And this establishes the second item in our theorem here. All the coefficients vanish and we are IMPA 0. So we have either uniqueness or a strong rigidity associated with all of the coefficients, and in that case, the solutions are positively proportional. Well, we will stop this lecture here, and in the next lecture, we shall resume with the analysis of solutions by constructing appropriate barriers associated to our generic equation.